away, it will disappear. Should I go back and start again now the recording has started, Nigel? Nick, sorry. Sorry, you think you might be on mute?
Yes, I am. I'm talking to myself, nothing unusual. Yeah, if you just want to very quickly just recap and bring it in. No, I'm sorry, I completely forgot to press the button.
Okay, no worries, starting again. So in summary, I'll cover antenna basics, which is the biggest part of the summary, but actually the smallest part of the presentation. And I'm going to talk about dipoles, short-loaded verticals, inverted Ls, and resonant loops, which is, I think, about as much as we will have time for tonight. So first of all, let's revisit what electromagnetic fields or waves are in free space. An electromagnetic wave consists of an electric and a magnetic field propagating through space. The electric and magnetic fields are at right angles to each other and the direction in which they are going. The ratio of the electric and magnetic fields is fixed, and you could sort of apply Ohm's law to it, as in voltage over current is resistance, and it comes out at 377 ohms, which is the impedance of free space. The electric and magnetic fields and the power density are in proportion to each other, and that relationship is fixed. And the power density follows the inverse square law with distance. In other words, if you double the distance, you measure a quarter of the power per square meter. And those waves are self-sustaining through space. They just decay as you get further away from the source and they spread out. And that is quite different from static electric and magnetic fields, that you get the magnetic field from a current in a wire that will deflect a compass needle near the wire, or the electric field that will make your hair stand on end if you get near a charged balloon. If you look at the field due to the current in a wire, so we have here a sort of orange wire, we have electric fields that spread out straight from the wire in all directions, and we have a magnetic field that if you put a compass needle near the wire and look at which direction it's pointing as you move it round, goes round in a circle. And if you go far enough away from the wire, you find that the electric and magnetic fields cross at right angles, which is the condition for an electromagnetic wave. When we come back to look at using software to simulate antennas, fundamentally what that software is doing is breaking up the antenna into lots of little short segments of wire and calculating the fields from each segment, and then working out how those fields add up at each point in space around the antenna. You can do this with pencil and paper and graph paper, but it takes a very long time. The elementary antenna from which pretty much all other antennas can be built up is the half-wave dipole. And if we look at the current distribution and voltage distribution in a half-wave dipole, so we have here our feeder, our feed point at the middle, because that's where we're used to it being, we find that we cannot have any current at the ends. It has nowhere to go. You have max, and the other thing I should probably say is that to work as an antenna, you need to have a standing wave. So if you pluck a guitar string and look at it, you'll see that the ends don't move, the middle vibrates if you just pluck it once and let the vibration die down. The same thing happens effectively with the electric current in the antenna. So you have a maximum in the middle at the frequency where it is resonant. And what we also have with an electrical antenna is we have a voltage which is at a maximum at the ends and a minimum at the center. And when you analyze antennas, you always, or certainly the way I was always taught to do it, is start with the ends because you know you have zero current, and then work back quarter waves to where you have a current maximum and a voltage minimum, and you plot the current and voltage distribution, and then you can analyze the antenna from there. The impedance at any point in the antenna is the ratio of the voltage to current. One of the things that you realize is because there is no discontinuity in the current, even at the feed point, you can move the feed point towards the end, and all that happens is that the impedance of the transmission line to match changes according to the ratio of the current to the voltage in the antenna. And that's why off-center fed dipoles work. It's still the same dipole, it still has the same current distribution, you're just exciting it at a different position on the string. So you can think of it with the guitar again, you pluck the guitar at one end where the sounding box is, not at the middle of the string, and it still makes the same note. The highest impedance, so next to no current, high voltage, is at the open ends. The lowest impedance is at the center of the half wave, a quarter wave from each end, and is about 75 ohms. The last thing I want to mention is field regions, which is more to do with EMF than radiation patterns or antenna gain. There is what's called a near field, which is close to the antenna, and a far field, which is 2 wavelengths and further away from antennas. Actually, that is not quite true. It is 2 wavelengths away if the antenna is relatively small. If the antenna is bigger than a wavelength, something like a dish or a broadside array, like a radar, VHF radar antenna, then it is actually determined by the aperture of the antenna and is much, much bigger. But for electrically small antennas like half-wave dipoles or quarter-wave verticals, it is 2 wavelengths away or less. In the far field, you have propagating electromagnetic waves. All of the individual contributions from separate elements of the antenna have combined, and you have the sort of far field radiation pattern. Closer than that, there are 3 zones. There is what's called the reactive near field within a 1/6 of a wavelength. This is where the EMF calculators dare not go, because they cannot treat the antenna as a point source anymore, and you have to add up the contributions of each element separately. Within that zone, you have inductive and capacitive coupling. You have parasitic coupling between elements of a Yagi, for example, and that is where induction systems that are not truly radio, the sort of things you have for hearing aids in churches and concert halls, work. And that will work over a surprisingly large distance. William Preece, who was the chief engineer of the post office in the 1880s and 90s, worked extensively on this, and he was able at a frequency of 192 hertz to operate an induction Morse system from Cardiff to Flatholm, which is a distance of about 3.5 miles. But if you actually look at it in terms of wavelength, it's much, much, much less than a 1/6 of a wavelength, and not at all surprising that it worked, which we know now he didn't. Between 1/6 and 1 wavelength, sorry, I should also say in the reactive near field, the strength of the field falls off very rapidly with the cube of the distance. So double the distance and 1/16 of the field, sorry, 1/8 of the field strength. In the radiative near field between 1/6 and 1 wavelength, the field's reduced with the square of the distance. So electric and magnetic fields reduce double the distance, quarter the field, or in terms of power density, double the distance, 1/8 of the field. And there is a transitional near field between 1 and 2 wavelengths where it becomes more and more like propagating electromagnetic waves in the far field. You will find with things like the simple Ofcom and RSGB calculators that they are accurate in the far field, fairly accurate in the transitional field, they will overestimate significantly in the radiative and reactive field areas, which is why it is worth doing simulations or calculations that are able to add up the contributions of individual elements and are aware of the rapid falling off of near field strengths. So how do we analyze antennas properly? There are three ways of doing it. The way I was taught at university involves the equations of Maxwell and more mathematics than I ever enjoyed. I passed an exam in this about 30 years ago, and I haven't done it since. But there are very clever engineers who are more of a mathematical than a practical kind, perhaps, like John Krauss, W8JK, I think he was when he was alive, who have documented how to solve the basic equations for lots of different antenna geometries. And I still have his book. That book has lived with me since my second year at university, and is, of all my university books, is the one that I read and reread the most. Basically because he's done the hard sums, so I don't have to. And you can do those calculations and work out the field at a point in space from first principles, but it is hard. Another very good engineer, Reg Edwards, who worked in his youth at the Royal Signals and Radar establishment at Malvern, turned a lot of those mathematical equations into computer programs in the 1980s when the IBM PC first came out. And the G4FGQ programs, you can type in the details of your antenna for various antenna geometries, mostly HF, and it will dutifully tell you things like the radiating efficiency and the impedance and the matching components that are needed. And those programs are still very good, or even if you need a MS-DOS emulator to run them on any modern PC, they are wonderful programs, and I recommend them to my friends. If you don't have a program that will do exactly what you want, then you simulate. There are a number of antenna modeling programs, paid and not paid. The best free program is a thing called the Numerical Electromagnetics Code. NEC came from Lawrence Livermore National Laboratory in the United States, who know a thing about numerical simulation because their day job is testing things that go bang, which they aren't allowed to do anymore, so they have to do it all by simulation. So they have a great deal of experience in numerical modeling for all kinds of physical problems. And in the 1970s, they developed NEC, we believe now, primarily as part of the early American work on stealth aircraft. And the versions up to version 2 were released as public domain software. Later versions are export controlled and have license fees. They're just a little bit too good. But NEC2 is quite good within the limitations that it can't deal with wires passing through ground. So it's difficult to model things like buried coax feeders. And what you do with NEC is you produce a 3D model of your antenna in the simplest way by drawing it on graph paper and then keying the coordinates into a text file, or when I started, punching cards and feed to your mainframe. It will then calculate the current distribution in the antenna. Given the current distribution, it will then plot the impedance versus frequency, the electric and magnetic fields close to the antenna, and the far field polar diagrams and gain. The polar diagram is gain versus bearing, effectively. Again, when I started, this came out as a text file, and you then fed that to a pen and ink plotter. Nowadays, various people have written Windows programs that capture the 3D model, feed the coordinates into NEC, and then take the output tables of numbers from NEC and produce the graphs. And I use a thing called 4NEC2, which was written by Iain G0OZS in the Netherlands. Others are available. You will hear of things called MMANA-GAL and ESNEC. They use the NEC core software, but charge license fees for what they have built around it, whereas 4NEC2 is completely free. ESNEC will do very simple antennas with the free version. MMANA-GAL will do complex antennas, but won't do near field plots unless you pay the authors for an add-on module. So let's have a look at, first of all, to build some confidence, an antenna that we're all familiar with, which is the 80-meter dipole, or any dipole in free space. So think of this as being two whip antennas stuck to either side of a satellite orbiting sort of a few hundred miles away from any conductive object of any size, as an extreme case. So our CAD model is a simple straight line with the feed point in the middle. Very, very simple. Basically, one wire with a voltage source halfway down. And NEC gives us the expected field pattern. So we have two big lobes broadside onto the antenna, and endwise it radiates equally all round, looking into the end of the antenna. And probably we remember this from our AE classes long ago. What happens if we actually take the dipole home and set it up over our garden at some practically achievable height above ground? This is actually my main HF antenna model, so this is what I did for the EMF. Oh, I should probably, before I go on to that, I was going to say that is the near field pattern for the dipole in perfect free space. To give some scale to it, those blue blobs are 25 meters long. Sorry, correct that. Plus or minus 25 meters. So 50 meters long and 8 meters wide. And the magnetic field is strongest near the middle where there's more current. The electric field is strongest at the open ends where there's high voltage. And what you will see is that if that's 8 meters from here to here, 4 meters from there to there, the ends for a 100-watt station, if you like, the safety distance is about 1.5 meters. The pink contour is maximum field effectively, and I set that to 83 volts per meter, which is what you need for the ICNIRP 6-minute power. So if we take it close to the ground, my antenna at home, the ends are about 4.5 meters up. The middle is on a telescopic mast that goes up to 6 meters. So there's our model. 2 wires, actually, for reasons to do with how NEC works, as a third minimally short wire in the middle that contains the feed point. And the 2 ends are bent down so that the ends are 4.5 meters off the ground. We first of all have a look at the far field. And what we find is that it is a very good radiator straight up. This is an NVIS antenna, primarily near vertical incident skywave. There is no gain worth having flat to the ground, and it has about 2 dB of gain relative to isotropic straight up, and a bit more than. And if you go round to say 15 degrees off the ground, follow that circle round, it's about -8 dB relative to a dipole. It's rubbish, basically, for DX or for local ground wave stations, because it has very little radiation parallel to the ground. And sort of remember that sort of -8 to -12 dB at horizon level when we come to look at the inverted L later. Horizontally, it radiates pretty much all round. It's not a very inverted V, and it's more to do with being close to the ground that does this. And if we look at the fields, what you will see is that the high electric field is displaced downwards towards the ground. And actually, effectively, for my station, which can run up to about 200 watts, it works out that 4.5 meters minus 2.5 meters, 2 meters off the ground is just achieved at the ends, but it is achieved. So I don't have to get it any higher. The other thing to note is that because the electric field limit below 10 megahertz is fixed and low in proportion to the magnetic field limit for EMF, it's always the electric field on low frequency antennas that determines the EMF safety distance. If we now have a look at a vertical dipole, you'd think that having the dipole vertical would restore the pattern because it's then not going to interact with ground. In reality, that isn't quite true because you have ground reflections and parasitic radiation from the mast. So this is what I use with my Land Rover for 6 meters, which is basically an end-fed vertical dipole. I built an NEC model of the Land Rover, which also has 4 and 6 meter wing antennas. It's an old Army lightweight. This is the main screen of 4NEC2. It will helpfully tell you the impedance at the feed point, the compensating components needed to match the transmission line impedance you've given it. So 4NEC2 adds a little bit of value interpreting the results when you run it. I've set it up with what they call a fertile land ground, which there is a table of different ground conductivities and ground dielectric constants for everything basically from salt water to sand. And that makes a huge difference, particularly to fields between the antenna and earth and real ground. And you can also model a perfect metal plate ground if you really want to. So I've gone for fertile land, which is typical of the sort of rich, muddy soils we have here in North Suffolk. If you're somewhere in East Suffolk on the dunes near the coast, you would use a much less conductive ground, which changes things a surprising amount. And what we see with this antenna is that being a vertical dipole, it has quite good low angle radiation, so it's still delivering 0 dBi to 2 dBi right down to about 5 degrees above the horizon. But it doesn't have anything like a dipole pattern. There is effectively nothing below horizon because of ground reflections. And this is fairly typical of things like collinear and end-fed dipole antennas on a mast over ground. The bottom half of the radiation pattern, it turns into reflections, which pushes the radiation pattern upwards, or the peak gain upwards above the horizon. What was actually much more interesting about that model, I modeled the Land Rover as plates and rods for the roof frame. I kind of expected parasitic radiation off the antennas on the wing boxes, which happened. What I wasn't expecting at all is that the mast actually acts as a collinear element, and that purely works from the electric field off the end coupling into the mast, because I modeled it actually isolated from the mast. And what you find is that because it's a 6 meter antenna or 6 meter half wave antenna and a 6 meter metal telescopic mast, you get effectively 2 half-wave dipoles fed into it. That one, I think, is actually the magnetic field, so it has the peak in the center of each half-wave. If it was electric field, it would be the opposite way around. Obviously, similar thing looking at the front of it. So you do, something to be aware of is you do have to think quite hard about parasitic radiation from anything that is close to half a wave or multiples of half a wave in size, even quite a long way from the antenna. So let's have a look now at what I use for top band. Obviously, these are antennas I've done earlier, as Blue Peter presenters used to say. So these are my antennas in the main. I use a base-loaded vertical for 160 meters. So it has 4 5-meter radials that are actually slightly closer together at this end than here, because that fits my garden, which is very long and very narrow better. I only have about 20 feet wide, but getting on 200 feet long. So to keep it a couple of meters away from the fence for reasons that we will see, I orient the radials that way, which makes a surprising amount of difference. Our spike in the ground, fiberglass pole over the spike, and the loading coil is about 1 meter up the antenna so that it doesn't have a metal spike through the middle, which might not make it work any better. And the feed point is more or less is a little bit below the coil, which works out at 90 microhenries to get it resonant at the top end of the 160 meter band, and I let the ATU drag it down to whatever frequency in the band I want, because my ATU is an ex-military one that basically likes electrically short antennas only. First of all, we do a impedance plot over frequency. Usually when I'm doing an antenna design, I start doing this and I adjust the loading coil or whatever other matching components are part of the antenna to get it on frequency as a first stage in optimizing it. Once you've got it resonant on frequency and reasonably well matched to the intended feed line impedance, 50 ohms in this case, I just have a 1-to-1 transformer at the feed point, mainly to get a DC path to earth for static. I then do the polar diagram, and you'll see again, this is very good at low angles. So it doesn't have good gain overall. It's about minus 16 dB at the best angles of radiation, which are around 15 to 30 degrees, but it does have significant gain down to 5 degrees. And I do hear quite a lot of very distant stations on top band because of that, and a lot of distant thunderstorms, unfortunately. Very little straight up, no envis to speak of. But it works very well for local top band nets that I go on Friday afternoons out to 20 or 30 miles ground wave, which is mainly what it was built for. Omnidirectional, as we'd expect. If we actually look at the near field, the slight asymmetry, just moving those ends closer together, results in a distinctly lobed radiation pattern above ground. The radials are hot for about 1 meter around. I think from memory I did that with half-meter squares. And looking at the vertical pattern electric field, it's slightly different because this is a truncated antenna. This is 8 meters tall. A quarter wave on top band would be 40 meters. So you're only seeing effectively the 20% nearest the end. So you have a big E field even at ground level. And that basically, if there was anyone else around, it would need a fence around it about 2 meters out, discounting the radials, of course. So I think the takeaways from that is if you shorten an antenna, you effectively get the pattern starting from the open end back towards the feed point in the near field, and above ground radials are hot all the way to the ends, especially if they're electrically short. A lot of people use inverted L's and think that they are much better than dipoles, particularly when working a mixture of distant and remote stations. So this is a model of one that I did earlier that had two resonant radials, one for 40 meters, one for 80 meters. The antenna, of course, is a little bit shorter than the radial for 80 because it goes up before it goes along. It's a quarter wave on 80. And what I had was a link that I could open to make it a quarter wave on 40. So just lower this end, disconnect the link, haul it up again. And it works quite well. Subjectively, it did work better than the dipole for some distances, particularly middle distance. And I had an automatic ATU about a meter off the ground. So with the radials hanging down from it. And this was the far field pattern. It is distinctly skewed with more gain strangely off the back, the end away from the horizontal wire. So down here or out here, it has better low angle in one direction, more high angle in the other direction. What is interesting is that although most of the antenna is horizontal, most of the actual radiation comes from the short vertical piece. And what you find is that it has gain of, if we remember that we were about -8 at low angles, here we're -6 down to about 15 degrees and about -10, almost flat to the ground. So these things have much better low angle gain, but much less high angle gain and very little off the top. So they behave very differently to a dipole. And my experience with these antennas, and I also actually had a extra piece of wire that I could use to extend it to top band. And the greatest distances I've ever got on top band, which is Cologne in Germany, was using the 160 meter version of this. It works well for ground wave. It works very well for very long distance sky wave. It is pretty hopeless for NVIS because there is very little goes straight up. Even though the dipole has more gain, most of it is going to heat the ionosphere is the conclusion. Unless you can get the dipole well clear of the ground. And looking at the near field patterns, this is actually at ground level because I was mainly concerned about the radials, and the resonant 80 meter radial has more or less a dipole-like pattern for electric and magnetic fields. The non-resonant radial for 40 meters on this band just basically has some electric field all along its length, which is fairly typical of non-resonant counterpoise wires in antennas I've looked at. The last one I want to look at tonight is the resonant full wave loop, which was done by special request. This is a fairly simple antenna. It's fed from the middle of one side. Depending on which article you look at, the ARRL Skywire or various other articles that I've seen in British and American journals, it's fed either with coax or with 450 or 300 ohm feed lines, and usually if it's coax, it has something like a 2-to-1 or 4-to-1 balun at the feed point. The circumference should be one wavelength on the lowest frequency in use. And I actually did this for the middle of the 80-meter band. And I made it 5 meters off the ground, which is a reasonably achievable height. I did actually have a friend who has one of these in his garden in mind, and I know roughly his supports are 5 meters off the ground. First of all, we had a look at the impedance. At the fundamental frequency at 3.65 megahertz, it is about 100 ohms, which is much lower than you would think reading some of the articles that talk about using 300 or 450 ohm feeder. And we can see that it's resonant with slightly worse SWR up to about 4 to 1 as you make your way up the harmonically related bands. So 7 meg, it's about 2 to 1. 14 meg is about the same, maybe even slightly better. There is something at 18 meg. 21 meg, it's 4 to 1. And it is beginning to show signs of matching if you go a bit towards the high end of the 10-meter band. And if you look at the impedance graph, so the resistive part of the impedance is the blue line, what we find is that it's about 200 ohms on the second harmonic, and most of the other harmonics, it's somewhere around 200 ohms up to about the fourth, and then it starts to go up to about 400 ohms. So I suspect the people who say feed it with 300 or 450 ohm balanced line really are thinking of using it on the higher harmonics. And if you're mostly oriented towards sort of 10, 15 meters, you'll say 450 works best for you. If you're more used to 40 or 20 meters, you'll probably say 300 ohms works best. And if you're mostly using it on the fundamental, you'll probably think that 75 ohm coax wouldn't be too bad. If we look at the patterns, I've plotted the vertical and horizontal patterns for the bottom 3 bands, effectively 80, 40, and 20. And what you see is a pattern similar to a long wire. As you go up to each harmonic, the pattern gains another lobe. The reason it has gone slightly offset is actually a major thing to note with these. If you set them up for the middle of the 80-meter band, you find that the harmonics are off the top end of the 40 and 20-meter band. So if you think 2 times 3.65 is rather more than 7.2. And certainly if you twice 3.8 is a long way above 7.2. And the same thing is true as you go up to 14 meg. So what you tend to find, and the effect of that of not quite fitting a full set of standing waves in, it's rather than 3, it's actually 3 and a little bit standing waves, is you get a distorted pattern. And you see the same thing in the horizontal plane, perfect on 3.65, not quite right at 7.1, is beginning to skew off to one side a bit, and it's very noticeably skewed, as well as gaining extra pairs of lobes by the time you get to 14 meg. So it is a compromise antenna, and you are probably best, if you're primarily going to use it on the higher harmonics, to optimize it for something down in the CW end of 80 meters and live with it being less than perfect towards the top end of 80. Let's have a look at the fields on 80 meters. So as we expect, we have basically 2 half waves here. So we expect current maximum and therefore magnetic field maximum halfway along each half, and we do have that, and they're nowhere near the pink, which is the IC and IRP limit. This is 2 meters above the ground for an antenna 5 meters off the ground. So at head height for a tall person, it's fine. And there's no pink even on the 4 meter. Actually, I'm telling fibs. I said this is the electric field graph. I take that back. So that's the electric field at 2 meters above the ground. That's the electric field at 4 meters above the ground. So in other words, if you lowered the antenna to 3 meters, give or take the effect of being closer to the ground, concentrating the field, so it's not quite scalable, you would see that you still have no pink. So that is actually pretty good at 100 watts. So it's a very nicely behaved antenna because it has no open ends. And I did do the magnetic fields, and again, there's nothing measurable almost at 2 meters off the ground, and only something very faintly measurable at 4 meters off the ground. And note the 2 sides that have strong electric fields are opposite to the 2 sides that have strong magnetic fields. So that was really the end of today's presentation. Obviously, the credits to the people who developed the software. NEC2, which is the core calculator, was funded by the United States government for initial purposes we can now guess at. It was developed primarily by Mr. Burke and Mr. Poggio at Lawrence Livermore National Laboratory and has been maintained by others since. The last public domain version is NEC2D, which is what I am using. There are later and better versions which are export controlled and have, I think it's $120 license fee for NEC4. And the visualization and input software I use is for NEC2 by Iain G0OZS, which has been available in various forms of free software since 1995 from qsl.net/4NEC2. And there ends the presentation for today. I think you're on mute, Nicholas, again.
Yes, I was just getting to do that. Yes, okay, and well, thank you very much indeed for that. I found that quite interesting, well, very interesting actually. As I said in my email, I'm not from the electronic world, quite the social sciences is my area. So this is things that I knew a little bit about, but you've really expanded upon what on my knowledge and built on my knowledge. Has anyone got any comments? Have you, Simon? You're normally, or Eddie, or Gary, you got any, or Remus, come to that? Any comments to make?
I've got a comment. The more I think I'm going to look at this is the less likely I'm going to want to build any antennas after I've tried them through the software. I've also got a long and thin garden, not as long as your one, I don't think. But can you do that that one you were just showing? Has it got to be a quarter wave on each side, or can you do like 3/8 down 2 of the sides and then shorter ones on the others? It
will affect the radiation pattern, but it won't affect the resonance unless it's ridiculously short. So yeah, I mean, my friend probably has his one is probably about twice as long as it is wide.
Right, I think I'll need to get the software downloaded and try a few things. This is very interesting, but I like everything to be perfect. We don't live in that world, do we, as far as the antennas go?
No, so I mean, the trouble is that these models are basically for an open field site with no wire netting fences and telegraph poles and telephone drop wires and things like that. And of course, if you think all of those are close enough within a 1/6 of a wavelength, probably on 80 meters, to be parasitic elements in their own right. So quite apart from EMC and EMF, they act as antenna elements and change the radiation pattern in ways that you have to think about.
Yeah, thank you. I'm going to download it and try it.
You got a question, Eddie?
Yeah, I've got a couple actually. First one, you've talked about 160 meters and 80 meters and said approximately sort of 2 meters, very rule of thumb. Does this will it still be about 2 meters on 40 meters, or does it start to climb rapidly?
Because the 83 volt per meter limit is constant basically from about 1 megahertz to 10 megahertz in IC and IRP, it's basically a power driven limit at the end of you will have similar field strengths at the end of a dipole or quarter wave, whatever frequency you're on for the same power level at the end of the elements. So what you are going to, so that effectively the electric field strength is driven by the voltage at the end of the elements, which is determined by the power going in. So 2 meters, 2.5 meters is probably right for 100 or 200 watts. Because it's a cube law that close to the antenna in the reactive near field, it falls off very quickly with distance. So I think the problem you have with EMF below 10 megahertz is you can't claim averaging. So once you go over 10 megahertz, the power level you have to calculate for is the average power level having regard to the transmit receive ratio and the modulation that's being used. So the distances come down very quickly because of that in practice. Below 10 megahertz, because there is a concern over nerve stimulation by electric fields, which effectively is something that acts instantly rather than accumulates over time, there is no averaging. And the 83 volts per meter is thought to be the threshold where those effects can be felt. So effectively the distance limit is only determined by power and the antenna geometry. So if it has open ends, you need to keep that far away, below 10 megahertz. I run an old marine radio, a Scanti 8255 as my main station, and that is good for about 200 watts on 80 and 40. So for me, 2.5 meters is right. And that agrees very closely with the RSGB pre-assessed configuration. I think they are a little more conservative than I am, but given that the displacement of the pattern downwards is very much determined by the choice of ground, I think there is probably a 50% margin of error there. I mean, at the end of the day, without actually measuring it, and only Ofcom are likely to be able to afford a calibrated field strength meter with a current calibration certificate. I mean, Mr. Rode and Mr. Schwartz will smile all the way to the bank account, to the bank if you buy one. So there is a fairly large margin of error. The other problem, I mean, when I've modeled it, if you model it over sandy ground, it's about 1.5 meters. If you model it over sort of wet salt marsh, then it's probably 2.5 meters plus something. So the more conductive the ground, the more the pattern is displaced downwards with low dipoles. So I think the RSGB have probably made different assumptions about the ground from my model, and both will be equally valid in their place. The other real world thing is the ground is unlikely to be uniform over 40 or 80 meters of horizontal distance. So I have effectively packed gravel near the house, and I have waterlogged ground at the back of my garden, which is about a foot above the River Dove that runs along behind my property. So I suspect in reality that if Ofcom ever do come and test their field strength meter, as long as they're near the house, I'm laughing. If they want to sit at the back of the garden after it's been raining for 3 weeks, they will probably have something to say.
Yeah, well, that's fine. The main reason for asking was if you run the current calculator at 30 meters, you get 4.7 meters for 100 watts.
Yeah, the trouble is that they are taking a formula that is designed for the far field and trying to apply it within the radiative or reactive near field, and that overestimates massively. So if you actually take the calculator and do what you find and compare it with other methods like this or the ARRL, the ARRL came here in 1998 when the FCC did something similar to what Ofcom have done now. And the ARRL, there being no internet to speak of back then, or not for the majority of amateurs, did what the ARRL always do and published a book. And they published a book of tables. So if you remember your math tables from school, they basically published a book of tables of distance and power for a great many kinds of antennas. And they did that jointly with the Federal Communications Commission and with support from the people who developed NEC, Lawrence Livermore. So we can assume that their results are reasonably accurate. And because they were interested in printing a book quickly and cheaply, they just published tables of numbers for the separation distance rather than graphs. And their results are very, very similar. They're not directly transferable because they didn't have the 83 volt per meter flat limit in those days. It was a frequency dependent limit below 10 megahertz. So their calculation isn't exactly the same as ours, but in most cases, the ICN IRP 98 was more conservative than ICN IRP 2020. So you can still use their calculations if you know what you're doing.
Okay, that's fine. The other one, just a quick answer, it would be appreciated. With an antenna running elevated verticals, elevated ground planes rather, does it tend to mirror the signal downwards, or can we assume that it is relatively no signal under the ground plane?
Where I've done simulations of elevated radials, they effectively function as a strip line transmission line over the ground. So the E field and H field are actually concentrated between the radial and the ground. So what you find, if you on VHF or micro printed circuit board, you have like a track on one side of the board, a ground plane on the other, and most of the field is contained between them. It is a form of transmission line. The same thing seems to happen if you have a radial over the ground, that you will find a field all around the radial, but it is much stronger between the radial and the ground. The other thing I can't model with NEC2 because it doesn't deal with dielectric or wires crossing ground, but from calculation and from common sense, because the permittivity of the ground is higher than that of air, the fields are concentrated in the ground and stay closer to the wire. So burying the radial will ensure that the field stays away from the surface and stays away from the general public or members of the family. How deep is difficult to say for certain. I mean, what I've modeled over ground for like 100 watt level stations is that you need somewhere between 0.5 and 1 meter of separation if the wire is above the ground. Probably 0.5 meter is enough at 100 watts. And I figure that burying it by that much leaves a big safety margin because the field will actually stay closer to the wire under the ground. But it does depend on the ground. If it's sandy soil, it might as well not, or pure sand, dry sand might as well not be there.
Yeah, the sort of antenna that I was sort of inquiring about was like the trap vertical type of thing with tuned radials.
Yeah, so those will probably have significant fields around them, so they would be similar to my model of the 160 meter antenna with electrically short radial.
So very, very sort of rule of guesswork, as it were. They're going to need to be like 4 meters up, kind of thing.
I figure so, yeah. So that there will be.
Just as a sort of, you know, very sort of rough idea.
Yeah, because
Yeah,
the E
okay.
field at the end will be much the same as if they were a quarter wave. The magnetic field will be concentrated between whatever trap element is in them, or trap.
Yeah, so you could
or
actually
loading coil
treat
is
them
in
as an antenna lying on its side, really.
Yeah, they're just an electrically loaded short antenna lying on its side.
Okay, that's fine.
Right, has anybody else got any other questions for Iain tonight?
Yeah, I have one, please. What about long Yagi, something like a 23 SEMS Yagi, about 36 elements? At which point does it become safe, or is it the two wavelengths as you were mentioning?
Well, it will depend on the power. I mean, something like a 23 centimeter long Yagi is probably a case where you're better just treating it in the far field. And the Ofcom calculator uses a formula that is a valid formula derived from Maxwell's equations that calculates the field strengths in the far field beyond the two wavelengths. Using it closer than that will result in overestimations. But so I think in your case, because a 23 centimeter long Yagi will have very substantial gain,
yes,
you are going to end up several meters away anyway to get down to sensible field strength.
Right.
So
Okay.
I think I would. The Ofcom calculator is going to be giving you answers that are more than two wavelengths. It will give you accurate answers.
Okay. Thank you.
I mean, at the end of the day, two wavelengths on 23 centimeters is less than half a meter, so it's going to, the boom is longer than that.
Yeah, the boom's 3 meters.
Yeah, so you're going to end up probably with, I would imagine, depending on the power level, separation distances of the order of another 3 meters in front of the boom.
Right.
The other thing that arguably Ofcom have now added to their guidance notes. So new as of May guidance notes are actually pretty good compared with where they started. They have said that they do recognize that the calculator only applies in the direction of maximum gain. And you are perfectly entitled to plot the radiation pattern of your antenna and say the gain in the direction the public can get near it is not the 12 dB of the Yagi, it's more like 2 or 3 dB, or even minus something dB in one of the nulls, and use that to calculate the distance in that direction, or the safety margin in that direction. That's a perfectly legitimate thing to do if you are able to document the antenna pattern.
Yeah, brilliant. Thank
you.
So
for most people with a long Yagi on a pole, it would be completely senseless to use the maximum gain in the direction the antenna is pointing. My experience normally is you'll find that the maximum exposure of the general public will be probably at something like 60 degrees down from the horizontal. Is a distance where there's still some gain from the antenna, or so 45 to 60 degrees down, there'll be some gain from the antenna, and people can reasonably get that close. Usually directly underneath there'll be more or less a null.
Right, okay. Thank you.
Anyone else got any questions for Iain? Silence. It looks like you've answered all the questions then, Iain. So thank you very much indeed. You've done exactly what I hoped you would do, in the sense of you've gone a little bit further than Dave finished, and just taken it that little bit further. So we can now add what Dave's presentation to your presentation and get a holistic overview of antennas. And I really appreciate that. So thank you very much for your time tonight. I really appreciate that. And well, thank you very much. And now you can go and sort your greenhouse out.
Yeah, thanks. I mean, if your friend in France who wasn't able to join can give me the dimensions for his actual loop, I can rerun the model in a few minutes with the actual dimensions for him and drop you an email of that.
It's John Pierre, and he's F1 Charlie Fox Alpha, and I think he's 83 years old, but he's still quite active in experimenting with the radio. He was hoping to be here tonight, but unfortunately, I don't know quite how he fits into his locality, but he had to go to an event with the local mayor, so he had to withdraw at the last minute. But I will let him know, and what I might do is I might give him your email address if you don't mind, and then he can contact you directly.
Yeah, that's fine. I can do that for him.
His English is pretty good, but you do have to occasionally guess the odd one or two words, but he's pretty good.
No, and unfortunately, when I was at school, I had a timetabling conflict, so I did German rather than French, so I could also do engineering drawing, and
Okay,
so I struggle always with French.
But with John Pierre, you just have to talk slowly, and then he's all right. If you talk quickly, then he gets a bit lost, but if you just talk slowly to him, then he stays up. Right, has anyone else got any questions? Last time of asking? In that case, Ian, thank you very much indeed for tonight. Very much appreciated.
You're welcome.
And as I say, I've got it recorded, and when we finished, I'll cut it off, and then I'll make I'll speak to a friend, and we'll get it on the net, and then I'll let you know the link and everything, so you're kept in the loop.
Thank you.
Once again, thank you very much indeed.
Cheers. Bye.
Bye.
Yeah, thanks.
Thank you.
And I wish everybody else a very good evening.
Before you close it, Nick,
Yes.
just if I can just let everybody know, being as most of the SSTV crew are on,
Yes.
Wednesday and Thursday next week, ISS SSTV. I have sent the details to Golden, and hopefully there should be an email coming out.
There's already come out.
Oh right, it hadn't come when I came up here, so
Yes, Gordon sent that out about the International Space Station. So yes,
really good.
Excellent.
It's not on every. There is an attachment. Should be an attachment with it which shows which orbits they're expecting to be transmitting on.
Yeah, I think it's darker. It's all in black and white, but some of them are darker black and white.
The darker ones are the orbits that they're saying they're going to be broadcasting on.
Okay, so there we've got something to look forward to next week then. Okay, thank you very much. Thanks for sending that around, Eddie. That's great.
I literally came upon it by accident. I was looking at the status, and it gave the information, so it was a pure fluke.
Remus, does that mean you're away then? Sorry, he's put or have you got a question?
No, that one was upload.
Okay, okay, thanks very much. Yeah. Thanks for joining us, Remus. And as I say, I'll keep you in the loop, and if we do anything more, we'll let you know.
Thank you very much for that, Nicholas. Thank you, Iain.
You're welcome.
Okay then, if that's it then, thank you very much, everybody. I'll close the meeting at that point, and I'll see your smiling faces or whatever have you on future events. And once again, Ian, thank you very much. Excellent. Thank you very much indeed.
Thank you. Bye-bye.
Bye.
Bye-bye.
Yeah, thanks. Good night.